Everyone, my name is Pramod Beesal. I'm an IT Delhi graduate and currently an IRSME officer. This is our last video regarding microprocessors and microcontrollers, and in here we are going to discuss about the remaining topics like our interfaces, our input output and the interrupt controls, all those things. Okay, so when we talk about microprocessors, we have seen already the architecture as well as programming of 8085 microprocessor. In microcontrollers, the most widely used example is of 8051. Just like 8085, we use here 8051. And the difference is, the main difference between the architecture of a microcontroller and that of a microprocessor that we saw already was regarding the components that they have. Okay, so a microcontroller has microprocessor as its CPU, plus it has other components also. Okay, so let's take an example here of Intel 80X96 and we will see the basic core architecture of this particular microcontroller. Okay, so this is how it looks like. We are having a CPU. So CPU is basically this whole part. This is our CPU, and the CPU is consisting of several different units here. Okay, so what units do we have? We have a register file under which we are having register RAM. Okay, so this is basically our upper file here, wherein we are having the register based RAM, and then we are having a lower file wherein we have CPU SFR. SFR is special function register. Just like we discussed in our microprocessors, we are having the special function registers here, maybe stack pointer and all those things. Okay, instruction registers and everything. Then there is second unit in CPU itself. There we call that as RALU. The difference between a ALU and RALU is, here we are calling it as register ALU. Okay, so what is an RALU? I will just write the full form here. RALU is register ALU. ALU is nothing but arithmetic logic unit, so that's only ALU. So RALU will be having certain different registers, as well as it will be having ALU itself. Okay, so these are like different parts of it. There is a microcode engine which will be basically converting our main program into sub programs. Okay, so we have already discussed about microcodes, how we convert a complex program into smaller program bits, and then that will be used to execute the instructions. And then we have our ALU to carry out the arithmetic and logic operations. We have our master program controller. Okay, so the program controller that is in RALU is called as master program controller. Then we have a PSW. Okay, and a PSW is nothing but program status word. Okay, so when we discussed about our microprocessors, we talked about something known as flag registers. Okay, so flag registers, which also are known as status registers. Okay, so in case of a microprocessor, especially 8085, so 8085 has its PSW of 16 bits. Okay, so in that we will be having accumulator answer. I mean, in those 16 bits, 8 bits will be of accumulator and 8 bits will be of flag registers. Okay, so that is how we will be having a 16-bit PSW in case of 8085. But in case of a 8051, our PSW is of 8 bits. So that is only the flag registers here. Okay, so the flag register only is called as the program status word in case of a 8051 microcontroller. Okay, and here 6 bits are used. 6 bits are used. In case of our microprocessor, we had used 5 bits, right? For the flag registers, we used 5 bits only out of 8 bits. Right? Here we use the 6 bits. Okay, so that is basically our program status word. So that will be acting as a flag register here. Then we have other registers, our general purpose registers basically. Okay, so this all unit is called as the CPU. Okay, now there is a second part which we call as the memory controller. So it will be basically used to control the interface with our memory, writing, reading and all those things. So the main parts here are prefetch queue. Prefetch queue means it's like our data will be stored here before it is being fetched by CPU actually. Okay, so it will help us increase the process here. Okay, it will increase the speed of the process. Then we have a program counter, but this is a slave program counter. Okay, so that is the difference here. We have a slave program counter in our memory controller, whereas we have a master program counter in our CPU or our RALU. Okay, so this slave program counter will be already holding the address of next instruction. Okay, so it will be coordinating with our master controller, and it will be holding the instruction of the address of the next instruction. That will help again increasing the speed here, increasing the speed of instruction execution, right? And then we have our address registers, we have our data registers, and we have our bus controllers, like just as we had in our microprocessors. Okay, so that is the basics of any microcontrollers architecture. We are not going into the detail of it. Okay, so if you talk about other things here related to microcontrollers, then it is known as a IMC. Okay, now what is an IMC? Integrated memory controller. Okay, so IMC is integrated memory controller, because we are using a memory controller here, right? So it is an integrated memory controller. There is a memory controller integrated with our system. It can also be called as MMC. So MMC and IMC are both same, only that MCC, that is known as memory chip controller. Okay, so we can call it as IMC, we can call it as MCC. PSW we have already talked about, that is our program status word. Okay, ALE is something called as address latch enable. Address latch enable. Okay, so when we discussed about our 8085's architecture, I told you that there was A8 to A15 and then AD0 to AD7. This was working as address plus data bus, and this was working as a address bus, higher side and lower side, right? So whenever I want to use it as a address bus, I will be using a latch, ALE basically, and that latch enable means whenever my ALE is set to 1 or it's set to high, then it will be working as a address bus. Okay, and when I set my ALE to 0, it will be acting as a data bus. Okay, so data bus if my ALE is 0. So that is just a part of our microprocessor or microcontroller. Then we have our SP, that is our stack pointer basically. Okay, so we have already discussed how a stack pointer works in case of a 8085 microprocessor. So in 8085, the stack pointer will be incremented or decremented by 2. Okay, there will be an increment of 2 or a decrement of 2, but in case of 8051, that is our microcontroller, the increment or decrement will be by 1 bit. Okay, or by 1 digit, I can say simply. Okay, that is the basic difference between the stack pointer of a microprocessor 8085 and 8051. Now all microprocessors or all microcontrollers do not work same way, so we are very specific here that we are talking about 8085 and 8051. Okay, then we have something known as SID, which I have already discussed also. It is our serial input data. Okay, now I can give the data input in terms of a series also, means one after another, then it will be called as a serial input data, or I can fetch them simultaneously, or I can send them simultaneously, then it will be called as a parallel input data or parallel output data. So this is our serial output data. That is what we have our SID and SODs. Okay, so these are like main terms related to microprocessors and microcontrollers that we had earlier not discussed in detail. Now when I talk about the interfacing, so what exactly is interfacing? What do we mean by interfacing? So interfacing is nothing but transfer of data. Okay, so transfer of data between either our microcontroller or microprocessor, whatever device that we are using, and its peripherals. And its peripherals. What are peripherals? Peripheral means whatever device is attached to it on its periphery. Okay, so those will be known as the peripherals. So how exactly am I connecting my microprocessor or microcontroller with the peripheral devices, that can be output devices, input devices, that is known as our interfacing. Okay, so I am creating an interface between the processor or the controller and the devices. Okay, or it is basically used to create a man-machine interaction. Man-machine interaction means if we want to know what's going on, what's happening, what is the stage of our instruction, so we create what? A desktop, right? So on desktop I can see, so the desktop is nothing but an interface. Okay, that is our GUI. GUI means graphical user interface. Okay, we have that in our systems, like in our PCs and everything. Okay, so that sort of interface we can have so that we know what is going on, and we can see the data, we can see the position of the data. Okay, now when we talked about the control bus, I talked about these two lines there, read line and write line. So when it is read bar, means it is low active. Okay, what do we mean by low active? Then whenever I want my system to read a data, it has to be 0. Okay, so on 0 it will be active. Okay, if it is 1, then it will be inactive. Simply. Okay, so if I say that my read line is 0, means my system has to read a data. Okay, if I say my WR is 0, then my system has to write a data. Okay, so both of them are low active. Okay, so these both are low active in nature. Then from where my interfacing is happening, is it with input output or is it with our memory? Okay, so based upon that, we again, if it is 0, then it is from memory. Okay, and if it is 1, then it is from input output devices. Okay, so if there is a truth table which says that IOM, okay, and it also has our read and our WR. Okay, these are the three things mentioned in a truth table, and it says, let's say it is 0 and it is 0 and it is 1. Now what should be happening here? What is the meaning of this particular thing? It says input output memory 0, means the functioning is being done with the help of memory. 0 means with respect to memory. Then read bar is 0, means it is going to read the data. Okay, so it is reading data from memory. Okay, very simple, right? Now if I want to say that I want to write data to input output device or our output device per se. Okay, so input output has to be enabled. That will be enabled at 1. If it is 1, okay, then I have to write the data. So this has to be 0 and this has to be 1. So it will be basically writing the data to our input output devices. So that is how we basically interface with our external systems or our peripheral systems. Okay, now other than that, we had the buses also, the 3 control system buses that we call them. Okay, system buses, our address bus, our data bus, and our control bus, right? So these buses are also used for interfacing only with our systems. Okay, then one register is usually equal to 8 bits. Okay, so we have already seen that in our 8085 that one register can store 8 bit, and 8 bits are equal to 1 byte. Okay, 8 bit means 1 byte. So that is how we use the number of registers. We decide the number of registers, how many registers do we need to have in our system to store a certain number of memory. Okay, so we will see the examples of that also by the end of it. Now when I talk about the interrupt control section, because that word has come again and again, the interrupt. What is interruption? Interruption means now I am doing something and you suddenly stop me from here. Okay, you suddenly disturb my doing. That is interruption. I am interrupting something, or someone is interrupting my work. Okay, so interrupt control section is basically related to the interrupts, means whatever interruption a microprocessor faces while executing a program or executing an instruction. Now while microprocessor is executing a main program, let's say there has been a command given to the microprocessor and it is already doing its work, it is already executing the instructions there. But if a interrupt signal is enabled, suddenly an interrupt signal comes, then microprocessor will shift the control from main program. So it will stop doing the main program and it will start processing the incoming request. Okay, so it will stop the main program that it was executing right now and it will focus on the incoming request through the interrupt. And after the completion of incoming request only, the microprocessor will shift back to the main program. So that is how a interrupt work, interruption or basically interrupting circuits work. Okay, so if there is something urgent and my microprocessor is already engaged with something, then I will send an interruption signal that okay, stop doing whatever you are doing, focus on this particular thing first. If you are done with this, then go back to the program that you were solving earlier. Okay, so the different types of an interrupt are basically, number one, we can have a hardware interrupt. Hardware interrupt means that will be put onto the architecture of our chip. So we can have a hardware interrupt. Okay, so in case of our 8085 microprocessor, we have 5 hardware interrupts. Okay, there are 5 hardware interrupts. If I want to give their names, although the names are not important here, but still you can have them. INTR. Okay, then we have RST 7.5, we have a RST 6.5, we have RST 5.5, and then we have TRAP, T-R-A-P. Okay, so these are the interrupts in the hardware of our system. So when we see at the pin layout of any chip, there we will be finding these ports basically under these names. So they are our interrupt signals. Okay, there are 5 interrupt signals. Now, among all these, TRAP is our highest priority interrupt. Okay, highest priority. Means if at once there are more than one interrupts, then we have already said that interrupt will stop the main program. But within the interrupts, we are having a priority system, and the priority is this way. Okay, so that is our priority. Means the highest priority is of okay, this don't look at it. Highest priority is of TRAP 1. Okay, so if a TRAP interruption comes, then everything will be stopped at all. Okay, then second that we can have is our software interrupt. Okay, means we give the interrupts with the help of our program. Okay, that is our software interrupts. But software interrupt or a programmer cannot change or cannot alter TRAP interrupt. Okay, it cannot basically stop the TRAP interrupt. The programmer also cannot stop the TRAP interrupt. Otherwise, there are basically total 8 software interrupts in case of our 8085 microprocessor. Okay, another category, if you want to divide our interrupts in, then the third category we can call as maskable interrupt. Maskable interrupt. Okay, now as the name suggests, we can mask those interrupts. Okay, so those interrupts can be masked either with other interrupts or with the programming. Okay, so whatever interrupt that we can change basically. Okay, so that will be known as our maskable one. So that can be disabled by programmer. Okay, that is called as our maskable interrupt. Okay, and then naturally we will be having a fourth category here, that is non-maskable. Okay, non-maskable means the programmer cannot alter it, or programmer cannot disable it. Okay, the programmer can't disable it. Okay, and we have already discussed that TRAP is our non-maskable interrupt. Okay, we cannot disable, or the programmer cannot disable a TRAP interrupt. Okay, then okay, there is one more category. We can classify them again with the help of this. We call them as vectored interrupt. Okay, they will be called as vectored interrupt. Vectored means vector, just like our normal mathematical vectors. So if the interrupt has a specific location in memory. Okay, so if interrupt has specific location in memory. Okay, so if there is already a location given to the interrupt in our memory, then it will be called as a vectored interrupt. Otherwise, it will be called as a non-vectored interrupt, or I can say a poled interrupt. Okay, means there is no specific location for that particular interrupt. Okay, so that is how the concept of interrupts work with respect to our microprocessor or a microcontroller. Okay, we have a term which is called as ISR. So ISR basically means interrupt service routine. Interrupt service routine. Okay, so you can just remember the full form of this ISR. So it is the program executed in response to an interrupt. Okay, so whenever there is an interrupt in our system, what program is it going to execute? That is given by the interrupt service routine, or ISR. Okay, so that is already there with our system. Okay, the last thing that I was talking about was our memory, okay, and number of bits and the number of memory that we can have or our system can have, right? So I said this, that one line usually can carry 8 bits or 1 byte. It can carry 1 byte. Okay, so number of lines and memory of the system can be interrelated with each other. Also, I have told you that one register usually stores 8 bits. Bits to store what we use flip-flops. Flip-flops are something which can either have 0 or 1 as their state. So what is their state is basically our stored value. Okay, so depending upon our flip-flop values, we can have our registers and they will be used to store the data or the instruction. Okay, so I told you that one line is equivalent to 1 byte or 8 bits. Okay, so number of lines will be basically related to our the memory that our system can have. Okay, and we have already discussed that 2 raised to power 10 is basically 1024, that can be said as a kilo. Okay, so if I say 2 raised to power 10 bits, okay, 10 bits, then it will be 1 kilo bits. Okay, if I say 2 raised to power 10 bytes, then that will be equal to 1 kilobyte. Okay, so that is the basic difference that you have to remember, because bits and bytes are not equal to each other. There is a factor of 8 inside them already. Okay, 1 byte is equal to 8 bits only. Okay, then 2 raised to power 20 was equal to our 1 mega, right? 2 raised to power 30 is equal to 1 giga. That you can directly also remember it, because 2 raised to power 10 is almost equal to 10 raised to power 3. Okay, so from there you can remember it. So 2 raised to power means 10 raised to power 3, so 1 kilo. 2 raised to power 20 means 10 raised to power 6 means 1 mega. 2 raised to power 30 means 10 raised to power 9 means 1 giga. Or 2 raised to power 40 will be 1 tera. Okay, so that way you can remember them. Okay, so when I say there are n lines in my system, okay, let's say I'm having n lines in my system. My system is having n lines. Then how much will be the memory of that particular system? Okay, so one line can store how much? 1 byte, right? So n lines, in n lines I will be able to store 2 raised to power n bytes. Okay, that is a very simple logic here. N is equal to 2 raised to power n bytes, because each line can have a state of 0 and 1 and so on, right? So that is why 2 raised to power n. So for example, when we talked about our 8085, the address line was of 60 lines, right? Our address bus was of 16 lines. Now I can tell from here that what memory can my microprocessor store. Okay, and if I look at that, then that will be simply 2 raised to power 10, 2 raised to power 16. That can be said as 2 raised to power 6 into 2 raised to power 10. Now what is 2 raised to power 6? It is 64. And what is 2 raised to power 10? 2 raised to power 10 is our kilo, and this is byte. So 164 kilobyte is the memory of our 8085 microprocessor. Okay, just to make it clear to you, okay, if let's say in another example I am having 25 lines. Okay, so there is an example here that my n is equal to 25. There is 25 lines in my system. What will be the memory of this particular system when n is equal to 25? So the memory will be 2 raised to power 25. Now 2 raised to power 25 can I write as 2 raised to power 5 into 2 raised to power 20. Now 2 raised to power 20 is what? 1 mega, right? We have already discussed that. 2 raised to power 20 is 1 mega and 2 raised to power 5 is 32. So it will be 32 megabytes. Okay, or MB, I can directly say it, 32 megabytes. Okay, similarly I can do the reverse calculation also. What do I mean by the reverse calculation? Means I am having the memory, then I need to calculate the number of lines. Okay, for example, let's say the memory that I need in my system is of 512 terabyte, and I need to calculate the number of lines here. What will be the number of lines? So how can I do that? So 512 and terabyte, I can write it as 512 into 1 tera. 1 tera is equal to 2 raised to power 40, right? We said that 40. 1 tera is 2 raised to power 40, and 512 is equivalent to how much? 2 raised to power 9 into 2 raised to power 40, that is 2 raised to power 49 basically. Okay, so how much number of lines we will be needing in our address bus? 49 lines. Okay, so that will be our answer over here. So that way we can calculate a relationship between the number of lines and the memory that our system can store or that our system can access. Okay. Now if we talk about the previous year questions from the topic of microcontrollers and microprocessors. So the introduction part, we already saw certain questions. Now the remaining questions we are going to discuss here. Okay. So the first question is regarding RISC stands for with respect to microprocessor. So I think we already discussed it, the full form of RISC. Okay, we have done that. So that is reduced instruction set computer. Okay, so clear? Reduced instruction set computer is what RISC stands for. Now the next question that we had is in our 2018 prelims, and it says which of the following is not an addressing mode in 8085 microprocessor. Okay, so we already discussed the addressing modes of 8085. Immediate was there, indirect was there, register mode was there, but there was no segment mode. Okay, so our answer here is D. Segment mode is not there in our 8085 microprocessor. Clear? And the next question that was asked in 2019 prelims. So which of the following is one of the basic units of memory controller in microcontroller? Okay, so I have already discussed about the memory controller of a microcontroller, and we saw that microcode engine was in RALU, right? Microcode engine was in RALU. Master program controller was again in our RALU. Okay, a program status word again in our RALU. The slave counter, program counter, that was in our memory controller. Okay, so this is our answer, the slave program counter. Other way also, if you don't remember, then we already know microcode engine means some code has to be written there, so that has to be in our CPU or our ALU. Then program counter, so this is a master program counter, so main program counter is always associated with our CPU or our processing system. Then program status word, that is our status register, so that is also associated with our this CPU only. So there is only one option that we can have as our answer, that is slave program counter. Okay, now another question that was asked in 2019 prelims again. So there were 3 questions in 2019 prelims. Okay, so we'll discuss that later. Next question we are going to discuss here. So this was an assertion region question. It says function of ALU or arithmetic logic unit in microprocessor is to perform data manipulation. Is that correct? Do ALU perform the data manipulation? Yes, that is it. ALU do the data manipulation only. That is the only job of our ALU. Okay, either through the logical operations or through the arithmetic operations. Reason that was assigned here was a status register is where data for an input to the arithmetic and logic unit is temporarily stored. No, that is not correct, because there is a temporary register in our system. There is a temporary register in our microprocessor where we use which we use to store the data temporarily. So second statement is wrong and the first statement is correct here. Okay, now last question again of 2019 only, and it says which of the following ways is adopted to store the contents in program counter. Okay, now this question is actually quite tricky. Okay, so I have searched for the answers of this and the explanations here, because there is nothing like this. There is no method which talks about the storing the contents in a program counter. Instead, what we do in a program counter is it always has address of next instruction. That is the only thing that we have in our program counter. Okay, if the question was about our stack pointer, if it was our SP, then last in first out would have been our answer here. Okay, that would have been our answer in case of stack pointer. But in case of a program counter, I don't know why did they ask this question. In most of the places the answer given is LIFO itself, but that is for stack pointer, that is not for program counter. In fact, if you talk about the program counter, then it should be first in first out, because we are executing the program in a sequence. The values of the program counter are always increasing by 1, and that is how we have written the program also. So to my knowledge, it should be first in first out. Okay, but in many places it has given LIFO, but that is for stack pointer, not for program counter. Okay, and that too we can have different system inside of a stack pointer also, but for 8085 only that will be true. Okay, so well, that's all. Now our microcontrollers and microprocessors are complete. We are done with this topic. Next we are going to discuss is our PLCs. Okay. Well, thank you for watching and best of luck for your exam.